So, when the equilibrium constant is very small, the position of the equilibrium highly favors the reactants. That means the reaction doesn't want to go forward very much at all. It's very hard for that to happen. So when the equilibrium concentration is small and when you have relatively large initial concentrations of your reactants, your reactant concentration will not change significantly when it reaches equilibrium. So, assuming the reaction going forward, your value of X at equilibrium, or your concentration of X at equilibrium, is roughly approximate to your initial concentration minus whatever the coefficient is, equilibrium. This is approximately equal your initial concentration minus whatever you find X to be, so the coefficient there. So basically the equilibrium concentrations are roughly the same because the reaction is not going to go forward very much. In these types of problems, we're only looking for one major concentration. This will make more sense in an example, I promise. I know, almost all of them are. You still have to do, yeah, so you get to drop things off. But again, the organization process is the same. That's where the bulk of the credit comes from. Do you know how to do it? All right, so what we are doing is we are approximating the equilibrium concentration of the reactant to be the same as the initial concentration. In order for this to be valid, you have to follow what is called the 5% rule. So when you do the approximation, you should do a little self-check. So the 5% rule says if your approximate X, the X that you solve when you approximate, over the initial concentration times 100% is less than 5%, you can do it. If it's 5% or more, you have to go back and do it the long math way. We try not to do that. We're lazy for good reason. Shall we try one? Yes.
Is that over initial concentration?
Yes. All right. Okay. So here, look, K is really, really small. Now, I need to be... So look here. Here's our reaction. We're going to have to do a little bit of work here, but look at what we're given. We're given H2S only. So do we really need to calculate Q? No, we don't. The reaction's going to go this way because we don't have any of these. Right? We agree? Okay. Now, do we have molarity? Not exactly. We have to calculate it. We are given 0.0125 moles per 0.5 liters, which means our actual molarity is 0.025. So even though this is a gas, we're using molarity. So be careful about that. These problems get sneaky. Okay, so we know it's going to go to the right. So 2H2S to the right, 2H2 plus S2. Initial concentration equilibrium. Initially, we're only given H2S 0.025. 0 and 0. Now, this is the reactant, so it's going to get less by how much? 2x. Good. These are our products. They're going to get greater by x. No, this is a 2x. That's a 2x. So they're going to get greater. So 0.025 minus 2x, 2x, and x. We do still need to write our equilibrium expression. So that's going to be, even though we visually determined the reaction was going to go to the right. So we know that K is going to equal H2 squared S2 over H2S squared. Okay, now, do we agree that this is a really small number? Yes. And so whatever we find x to be is going to be very small, and it's not going to make that much difference when we subtract that, because this is significantly smaller than 0.025 by about 4 orders of magnitude. So when we're dealing with subtraction, that's not significant. So what we're going to do is initially go ahead and plug everything in. 1.67 times 10 to the negative 7th. So here we have 2x squared x over 0.025 minus 2x, and that's supposed to be squared. Now, the way you note this is you go ahead and you write it and you plug it all in, and then you go, wait a minute, this is gonna be highly in favor of the reactants. This is not gonna change much. So this is where you mark the X out in the reactant side. You say X is small, it's not gonna make enough difference to matter. So we're going to proceed now as if this X did not exist. It still exists up here, but it's not going to make much difference.
And we'll cross it out.
We are crossing out the minus 2x.
Will you explain that it's not very big because it's not going to change?
Yes, because this equilibrium constant is very, very small, right? So that means the reaction highly favors this side of the equation. Not very much is going to be making products. That's what a small k means. Very small k means reactants are highly favored. We're not going to make many products. Knowing that, this is not going to change very much. Note that the question doesn't even ask us to find that equilibrium concentration. It says, assume, let's find these others. So any amount that we calculate is going to be so much less than 0.025, it's not going to matter in subtraction. We'll check it at the end to verify that we are correct in making this assumption. But do this if you can. Look for X is small. This is called the X is small approximation shortcut. or the x is small shortcut. Use it anytime you can. We like x is small. We like it a lot. So now you can proceed to solve this equation as if this 2x isn't there, because it's not going to make much difference. So, do we agree that it makes it significantly easier to solve? Maybe. So 1.044 times 10 to the negative 10th equals 4x cubed. Do we agree that this is much easier to solve than the whole quadratic stuff? Yeah, do this if you can. Many problems work out this way. That's a hint. Okay, so now let's divide by 4. And now we need a cube root, which I'm too lazy to put that, so. Okay. Did we get a very small number for x? Yes. You still have to square this part. You still have to square that. It's just algebra you haven't done in a long time. Okay. So this is a really small number. Yes? Yes, this is a really small number. Okay. So I don't forget what it is. I'm just going to store it under a random letter. It'll be W for me. Because I'm gonna show you a few things here. All right. So using x, the way you can check it now to make sure that it's valid is you take your approximate value of x, which is this, divide it by your initial concentration, 0.025 times 100. This is less than 5. Approximation is valid. Rock on. If you don't want to use the approximation, go for it. Work out the hard math. It's not going to matter. So, this doesn't even ask for the equilibrium concentration of H2S. It only asks us for H2 and S2. So H2 is 2 times that. So 2, what did I store as W? 2.97 times 10 to the negative 4th. So that's 5.93 times 10 to the negative 4th. What are our units here? Molar, yes, molarity. Good. Now, according to rules of significant figures, which say when you subtract, in this case we're only going to get 3 decimal places, this isn't going to matter if you subtract that. So if I did 0.025 minus that answer, it goes down maybe by 1/1000th. Do we agree that that's basically the same thing? That's why you don't have to do the hard math. Shortcuts. Use the shortcut. The shortcut makes your life much easier. I don't expect you to fully understand it at this